Good afternoon, Dr. Curvis. Good afternoon, Hannes. We are the Botdells, and this is our final presentation. Following in the footsteps of the great George P. Burdell, our team is composed of the following members: Devin Pellegrino, Derek Gravitt, Gabe Lube, and Ajith Shajan. This past Friday was the long-awaited 2110 final competition. 61 teams worked relentlessly in the weeks before for a chance to be claimed the champions of 2110. This year's theme was based on the Georgia Tech experience. The goals were to collect good grades, remove bad grades, get sleep, and steal the tea.
In order to properly plan for this project, we used a house of quality which defines the relationship between the customer desires and product capabilities. The symbol shown in the middle of the table describes this relationship. The customer requirements represent the demands that must be fulfilled to earn the points in the competition. And the engineering requirements represent the methods used to meet these demands. As you can see from the customer requirements, determining the position of A and F, moving A block into the transcript, the safety of the machine operation, and the prevention of damage to the arena are considered to be the most important customer requirements, each with a rating of 10. For the engineering requirements, the weight, the cost, and the speed of initial deployment are the most important, each having a calculated relative importance of 10% or more. The function tree identifies the main function of building a winning machine and further deconstructs this function into simpler sub-functions. It is evident from this function tree that getting good grades will be the most time-consuming task due to the fact that this section of the tree is largest when compared to the others. The sub-functions from the function tree goes into the morphological chart, which shows the possible solutions for each sub-function. Using the drawings of the morph chart, we developed basic ideas of how we would accomplish our sub-functions. As we evaluated our alternate designs, we used our morph chart as a foundation of ideas and a helpful guide to ensure that we addressed all our functions. In order to determine the best design concept, an evaluation matrix was used to rank each of the 5 designs based on the most important requirements from our house of quality. The 5th concept was the highest scoring design by a good margin. This is because of its deployment speed in collecting the T and its consistency in retrieving the A back into the transcript. It results in an efficient way in scoring the most points.
Pictured here is our qualifying machine, of which our final machine was based. It was designed to accomplish 3 tasks: collect the A, knock away the F, and steal the T. The F arm proved to be fairly reliable, but we received a seat of 48 for 2 reasons, the first of which concerns the T arm. In order to fully reach the T's rotating on the center platform, we attached a hinge to the end of the T arm. This proved to be troublesome because the wooden T's could easily rotate the hinge, allowing them to pass without falling into our zone. Our second issue in the qualifying round was that our machine did not fully retrieve the A. A small lip between the base of the arena and the ramp leading up to the transcript, circled in red on the arena diagram showed, caused us much trouble. The A would often get caught on the lip and immediately fall over as an arm attempted to drag it into the transcript. This misfortune prevented our team from obtaining the 15 points associated with the A. Despite this challenge, the results from our qualifying round paved a road for success, as we were able to correct these problems when designing our final robot.
Our team's final machine is George P. Botdell. GP Botdell was designed to consistently collect the A, quickly extend an arm to collect T's, and efficiently remove the F from the designated area. Looking at our performances in the qualifying rounds, we were able to fully develop our initial idea for removing the F, as well as develop a more efficient and reliable method for retrieving the A and deploying the T arm. As seen on the right, GP Botdell's compact housing in the rear allowed for easy placement and access to all parts of the machine, making it possible to work on any part when need be. In order to complete these tasks, George P. Botdell consists of 3 main components: a 2-armed apparatus located on the top of the primary sliding body to retrieve the A, 2 separate F-removing arms, and a T-collecting arm mounted on the secondary sliding body. The 2 arms are held by a pin placed through a block between both arms. Once the primary body extends far enough, the pin is pulled via string and the 2 arms drop behind the A. The first arm's purpose is to pull the A until it reaches the incline leading to the transcript. Here, the first arm knocks the A onto its side and leaves it on the incline. The second arm then continues to pull the A up the incline and fully into the transcript. In order to account for the unknown letter locations, the arms are easily removable and can be flipped in the other direction. The system used to remove the F is very simple. The arm is initially pulled in by the primary body side and held in place with a pin. Once the primary body is extended enough, the pin is pulled via string and the mousetrap activates, swinging the F arm into the F, knocking it out of the zone. Each side of the machine has an F arm system, but only the side where the F is located is loaded. The T arm is located on a secondary sliding system. Initially, the extended arm is folded to rest on top of the main body, which positions a nail protruding out of the arm up towards the top of the machine. A plunger for the small solenoid is hooked into this nail. Once activated, the solenoid pulls the plunger in, releasing the secondary body to slide into the arena. Once the body extends far enough, a pin is pulled via string, allowing a mousetrap to flip an extension arm onto the rotating platform. At the end of the extension is a curved piece of plastic that acts as a guide in order to knock the T's into our team's zone. Seen here is a video of one of our machine's test runs. As you can see, the F is completely knocked from the zone. Then, the A is successfully brought onto the transcript, and all T's that pass the arm are knocked into our team's zone.
The machine did not perform as expected during the final competition due to various reasons. As a result, we were eliminated after 2 rounds. In the first round, we received 1 full T, 1 partial T, 2 Fs, and 1 medium pillow for a total score of 7 points. We tied for second place. However, the tie went to the team with more pillows, therefore placing us in third. In the second round, we received 1 F for a total of -8 points, putting us in third place ahead of the TA bot. There are several reasons why our machine did not perform as expected in each round. In round 1, our A retrieval mechanism failed to retrieve the A and place it in the transcript. The set screw in the motor coupler, circled on the left in red, slipped against the motor as it tried to pull in the main arm. As a result, the main arm remained stationary after it was deployed by the pneumatic actuator. This failure is likely due to over-testing of the device, as it performed fairly consistently during testing in the days leading up to the competition. Another failure in round 1 concerned the pin system in the F arm, circled on the right in red. Once the main arm extended a specified distance, a pin on the string is supposed to pull from the F arm, releasing a mousetrap which swings an arm designed to knock away the F. Unfortunately, the pin remained wedged in the screw eyes upon deployment, which prevented the F from exiting our area. The T arm, on the other hand, performed as expected and collected 1 full T and 1 partial T during round 1. In round 2, our machine failed to deploy. This is likely due to our faulty banana plugs. In between the first and second rounds, we noticed that the insulation in the middle of our banana plugs had been stripped away, leaving a few wires exposed. We did our best to fix the problem by wrapping the section in electrical tape, but it proved to be ineffective. Surprisingly, we avoided a disqualification because the drawer slides on the main arm just happened to slip, therefore causing the main arm to slide into the area. There are several ways to improve our design, the first of which is to fashion a new motor coupler and pulley. Our machine likely would have been successful in the final competition if the motor and pulley were properly fitted. The second improvement we could make is designing a pillow collecting mechanism. Our team faced constraints in obtaining both the A and the pillows, which made it very difficult to accomplish both. The third and final improvement is to replace our pin system with a more reliable alternative. And go Jackets!